Here are solutions to homework set number 12 for ECE 376 Embedded Systems. This homework set looks at filters, specifically filters in the Z-plane or filters implemented with a microprocessor. Now the first problem is, if I have a filter in the S-plane, what is the differential equation relating x and y? So S is the Laplace operator. What Sy means is the derivative of y. And where that comes from is Laplace assumes everything's in the form of e to the st. So when I differentiate, I get S times e to the st. So S means derivative. To find out the differential equation, just multiply the polynomial, cross multiply. Note that S means derivative, so S squared is the second derivative of y. Sy is the first derivative, and 12y is 5 times the derivative of x plus 5 times x. This is using Liebowitz notation. Lagrange used primes, Newton used dots. Different ways to represent derivative. The reason we like transfer functions is it makes filter analysis way easier. For example, suppose I have x of t is 3 plus 4 sine of 2t. I'm going to use the property of linearity. What linearity does, or says, is in a function with two terms, that's f of a plus f of b. So treat these as two separate problems. I'm going to assume x is just a constant 3, find y. Assume x is a sine wave, find y. Take the two answers, add them up. That's the total answer. So taking the first one, suppose x is 3. If x of t is 3, then the phasor representation for 3 is just 3. S is 0. Everything is cosine omega t. 0, constant, is like cosine of 0t. Cosine of 0 is 1. So this is the gain everywhere. All I care about is what's the gain at s equals 0, times the input at s equals 0, and to get a number. That is y of t at dc. Take the second term. In this case, x is 0 minus j4. Real part's cosine minus j is sine. S is j2. That's the frequency. This is the gain everywhere. All I care about is what's the gain at 2 radians per second, times the input at 2 radians per second. Gives me a complex number. Real part's cosine minus j is sine. The total answer then is your dc term plus the ac term. Problem 2. Suppose I have a filter in the z-plane. Well, z assumes everything is in the form of z to the k. What that does for you, if I move forward in time by 1, that becomes z times z to the k. So in the z transform, z means next value. Take this transfer function, multiply out the polynomials, cross multiply, and note that z means next value. So this is y 2 samples in the future, minus 1.5, y 1 sample in the future, plus 0.56 times the current y is 2, times x, 1 sample in the future, minus 0.9 times x. So this is the difference equation that corresponds to that transfer function. Some people like to do a time shift, just do a change in variable. I can shift everything by 2. This is also valid. Either answer is correct. The reason we like transfer functions is the same as the S-plane. Given a sine wave input, constant and a sine wave, I can use phasors and find the answer. So if x of t is a constant 3, then s equals 0. Z is e to the st. That's the mapping from the S-plane to the Z-plane. Wherever I have s, take e to the st, that's z. Here, s is 0, so z is 1. This is the gain everywhere. All I care about is what's the gain at z equals 1, times the input gives you 10. That's the dc term. AC term, same idea. Here's the input. In phasor form, it's 0 minus j4, 0 cosine, 4 sine. The frequency is j2. E, or z, is e to the st. That's 1 at 0.02 radians, or 1 at 1.4 degrees. This is the gain everywhere. Find the gain at that complex number for z, times the input at 2 radians per second, gives you a complex number. Real part means cosine, minus j means sine. The total answer then is dc plus ac, just like we did in the S-plane. Problem 3. The reason we like the z-transform is it's really easy to implement that in code. Just cross-multiply, multiply out the polynomials, and here's your difference equation. Solve for the highest power of y, the current value of y, as a function of the previous values, and there's my program. To implement this, I need to remember the current input, 1 sample ago, 2 samples ago. So there's 1 sample ago, 2 samples ago. The current output is 1.5 times the previous output, minus 0.56 times the output 2 samples ago, plus 2 times x, 1 sample ago, minus 0.9x, 2 samples ago. Presumably do something like spit out that analog voltage, wait 10 milliseconds, then repeat. So this is why we like z-transforms. Implementing that filter in code is really easy. The last problem is here's an application of z-transforms. Time value of money. Suppose I want to buy a Dodge Charger EV for $64,000. The interest rate is 6.74%. I'm going to pay it off in 10 years. What is my monthly payment? Well, the z-transform is the loan amount next month is the loan amount for this month plus interest. So here's 1 plus interest, 6.74% per year, 12 months in a year, that much per month. Plus how much I borrowed at k equals 0, that's a delta function, minus my payments. Now the payments typically don't happen on the first month or right away. I wait a month to make the first payment, so this is a step delayed by 1. Take the z-transform. Next value of y, current value of y, delta of k has a z-transform of 1. Step is z over z minus 1. Delayed step is 1 over z minus 1. Now solve for y. Do partial fraction expansion. Multiply both sides by z, because I need a z over here. Now take the inverse z-transform. So this is 6489 times 1.005 to the k minus 178 p times 1.05 to the k minus 1. Divide by z. That means delay everything by 1. All the k's go to k minus 1. And this is how much I owe at month k. For 120 payments, I'll have 0 balance at 121. 0 balance at 121 means I don't owe anything. The loan's gone. So plug in k equals 121. Solve. I get $744 per month. As a check, there are lots of mortgage calculators online. If I go to, for example, bankrate.com, here's my mortgage calculator, plug in those numbers, and I get the same answer. $744 a month, $744 a month. So that is, in a nutshell, z-transform. We'll use that next week to implement a filter. And that's homework set number 12 for ECE 376.